Hey everyone, welcome back. My name is Ujjwal, and today we'll be learning about regression, a different kind of machine learning technique on solving some type of problem. So, what regression is, let's try to understand it by looking at an example. Assume you want to buy a house, and you are looking at how the price is being determined over there. So, assume the price of the house of a particular house that you want to buy is either determined by the area of the land in terms of any like square feet or something like that, or it could be determined by the number of rooms that are available inside the house or something like that. It's all like subjective. So how do we approach this kind of a problem, when there are like multiple factors? Assume this could be one of your parameter. This is your one of your parameter. When I say parameter, it's basically a factor which determines something. This is a parameter 2 or something like that. Assume you have n parameters. So how do you use at least one parameter or more than one to determine the entire price of the house? So let's try to analyze like this. Assume we have some kind of an historical data which is being plotted over here. For now, we'll take the number of rooms as the example in this case. So of course, the y-axis has to be the price of the house. It can be in dollars, rupees, anything. And here the number of rooms is our x-axis. So now assume there is, 1, 2, 3, and so on. You can have these many rooms. And here we have, this is just for example. So 1,000 as your price, or 2,000 or 3,000, and so on. So what we can get from the data, assume this is just a data, I'm just making it up as of now. Assume the data is plotted like this. Yeah. So let me just correct a couple of points to avoid confusion. Yeah. Now, if you look at the data set, what can we try to analyze? What's the general trend? Since it was just one room, the price is between 1,000 and 2,000. And as we increase the number of rooms, the price is also increasing, right? So at one point, it's somewhere around 5,000, 5,000 USD or INR, something. So this is what is happening. So there's a general trend. What is the trend? It's like a basic uptrend. Yes. So you can think of it as an uptrend, something like this. I've drawn a random line which goes through most of the points, but you can see it's not touching any of the point. Assume I draw one more point here. Yeah, in this case, it's touching just one point. So why did I draw it like this? It's not representing every point, right? Because this point is clearly outside the line. This one is way off from the line. Like you can see the difference over here. So why did I do it like that? So usually, what do we try to do while predicting is we try to draw a line of best fit. So this line that you see here, this line, let me just reiterate over the line. Yeah, this line, the straight line that you're seeing here, is called as line of best fit. We call it line of best fit because it tries to satisfy most of the points while maintaining the distribution on either side of it in an equal manner. So in this case, you can see, for the one bedroom house, if the point was here, and what is the line trying to tell us? For a one bedroom house, if I draw a dotted line, if I try to draw that dotted line, it says it has to be 1,000. Like this is where it is intersecting. Yes. So what does that mean? According to the line, it says it has to be 1,000, but according to the actual data set, it is like somewhere 1,500. So there is some kind of difference here, right? So line of best fit. So what is it trying to do? It is trying to just maintain the data set, or trying to analyze the data set and find the line that best represents the entire data set. So we generally know the equation of a line. It's going to be y is equal to mx plus c, where m is the slope of this line and c is a constant wherein it intersects on the y-axis. Yeah, in this case, so now assume this is your y prediction, and what is your y actual or y expected it has to be for understanding purposes. So we'll just name it as y expected. So now let's assume we'll just take the one bedroom house as an example. So we'll say it has to be 1500 as our expected value over here, but it's coming as 1000 from this equation. So since we know there's a difference over here, of course there's some kind of a loss that occurs based on this line of best fit. So let's represent our loss as E for now, and this is going to be the y expected, or basically the absolute difference between the y expected and y predicted. So if we do the calculations, we get it to be 500 units. 500 units is our loss. But this loss is just for this one data point. Now, if we calculate loss for every data point, so we'll get all the losses, right? So we'll get like, assume your L1 is equal to 500, your L2 is equal to 250, and so on. You get, if there are 50 data points, your 50th loss is around 300, something like this. Then what do? You just add up all your losses, L1, L2, L3, and so on until L50. And then you divide by 50. Basically, this is taking your average of all the losses. So this will be your final loss, L or E, whatever you can represent. So what do we call this loss function as? What is it doing? It's taking the average of all the losses. So this is called as MAE, which stands for mean absolute error. So it's basically taking the absolute error for every data point and calculating the mean of it. So we're just calculating the mean here. So based on this loss, what does it happen? It tries to find another line of best fit. So it looks at the loss, then it'll be like, okay, I have to improve. Then it'll try to readjust its line equation such that it will try to reduce the loss in the next iteration. So assume this was your data set. The initial line, let me draw the initial line in this format. Assume this was your initial line. It just passed through like 1 or 2 points. Now this time it will try to pass this way. This time it was able to cover most of the points, but it's still not the correct representation. So in your iteration 2, your loss would have been somewhere like, assume in iteration 1 it was 1200 as your total net loss. In the second iteration it's around 1000. So this is kind of an improvement on the previous iteration. So this is how it tries to adjust itself. So what is it doing here? Since it's a straight line, we are trying to keep it as simple as possible. Since it's a straight line, what is it trying to do? It's just trying to adjust its C and M. You can't change X and X here because this is the independent variable. When I say independent variable, what does it mean? It means the variable that is a factor or a parameter that you're trying to use to determine an independent variable. Here the y, which is a price, is an independent variable, and here x, in this case, which is the number of rooms, is a dependent variable. So the only things that the model can change through iteration by looking at the mean absolute error. Remember, this is a loss function. We call it as a loss function or cost function. You can call it by many names, but usually it's called as loss function or cost function. Yeah, cost function. So it's only trying to change M and C here. In this case, at least. Of course, the model equation, the line equation can be more complex. But yeah, it's trying to change this, and it will try to improve such that the loss is at its lowest. Of course, we want it to be 0, but it's not possible in real world. So it will try to make it better and better through iterations. And at one point, it will stop learning, which means it has tried it's best to reach the lowest in terms of loss. That's when you can use this line. Now assume you have ran your model for multiple iterations and your data set is also good enough for the training purposes, and it has tried to find this line as line of best fit. Line of best fit. Now, what do you do is, let me just erase that part. Now, what do we do from this? The training is done. It has tried to fit itself to the data set, and it knows how to predict the prices to a certain extent now. So now what do you do? If this was, I'm just drawing the axes again. Yeah. And let's keep this as 2,500, something like that, and 3,000. Now assume you're looking for a two-bedroom apartment. And what do you do with this? How do you, predict? So assume your equation is y is equal to 20x plus 32. This is what it has learned after many iterations. So what do? You just pass in 2 as your input because you're looking for 2 rooms in this case. So y is going to be 20 into 2 plus 32. It's going to be 40 plus 32, which is going to be 72. Of course, this equation doesn't represent what is actually required over there. So let's just try to, make it reasonable over there, something like this. But you get the point over here, what's happening. So it's going to be something like 80 plus 320, something like 400 USD something. So what's happening is you just pass in 2 as your input and try to find the line that intersects on y-axis. So in this case, something like $2,400. Pardon this calculation because we just took a wrong coefficients, which is not a representation of the data in this case. But you understood what we are trying to do is we train the model such that it tries to find the line of best fit. This is the line of best fit, which tries to satisfy most of the points, trying to reduce the error between them. It tries to make sure the line represents all the dots, but of course it can't represent everything. It will try to represent the maximum of it. Then if you want to predict something on your own, just pass in your data and see where it passes through on the y-axis, or just plug in your data in the equation that it gives you, and from that you can get your value. So this is the entirety of linear regression. So what was this? This was actually called as linear regression. So the actual definition of linear regression, if we look on Google, so what is linear regression? Linear regression is a model that estimates the linear relationship between a scalar response and one explanatory variable. Okay, let's just go with the simplistic answer over here. So what is it trying to do? It is trying to find the relation between 2 variables. What are our 2 variables? Our variable 1 is the number of rooms, and our variable 2 is the number of price. Not number of price, it's the price of the house. So it is, the data set could be something like this. It's trying to find the relationship between those 2. So in this case, we are trying to find a linear relationship since the data set represents a linear upward trend. So this is what linear regression in gist. So this is what linear regression represents. So this is what linear regression is all about. And you saw, I mentioned a loss function, right? So here we saw a loss function, which was MAE. What is it? It's basically the absolute differences of, the mean of all the absolute differences, correct? So now assume you have a y true, right? Y true, and y true or y expected, and you're subtracting your y predicted. You're taking the absolute value of it, but this is just for one data point. You have to take this for all 50 data points, or how many data points you have, add it all up and divide by the number of observation. So if we try to generalize, I'll put a summation symbol here. I belonging to 0 to n points. Assume we have n data points. So we take the true value of the ith variable and the predicted value for the ith variable, and then finally divide this by n. So this is MAE. Then there are lots of loss functions that I would recommend you try exploring. There is something called as MSE. and RMSE, yeah, wherein MSE stands for mean squared error. So this is similar to what you saw in MAE. So if you look at mean squared error, you are just adding up all the, if you take y true of I and y pred of I, and you are also dividing by n. But the only difference here is you are just squaring each term. Yeah, you are just taking the square of each loss and then adding it up and then dividing by the number of data points. So what's the difference? Now assume in MAE, we'll just assume there's only one data point. Your loss came out to be 9. But in MSE, if we look at the loss, since we are squaring it, there will be a loss of 81. So why do we have to represent, why do we have to go through 81 instead of 9? When you show 81 as your loss to the model which is trying to learn, it will look at 81 as a very, huge loss and try to learn better. It is trying to give a penalty, in other words. So even if there is a small loss, assume your MAE was 3, but your MSC will be 9. So even if your loss is good enough for you to accept it, it's still going to show it as a huge loss, which will in turn trigger the model to learn better. So you are giving a penalty, in other words. And that's the whole purpose of using MSE. Then similarly, RMSE is basically same as MSE, but you're just taking root of it. So whatever your MSE value is, you're just taking a root of it. That's it. That's the only difference in this case. It's just to maintain dimensionality, because when you square the terms, right, in MSE, you're squaring all the terms. So if you square the terms, the unit of loss is going to be, in this case, like price square, like not price units, something like that. But if you take the root of it, the unit is still going to come back to price, which is same as MAE. MAE and RMSE dimensionality units are going to stay the same. So that's the whole point of this using RMSE more than MSE. But both are equally good functions. You can try out multiple functions through examples to understand how they work. But that's it for now. Thank you for tuning in. Welcome back. Before we wrap up regression, let's also look into another type of regression called as logistic regression, which to give a formal definition, we'll see what it means. Yeah. So it says in statistics, the logistic model is a statistical model that models the log odds of an event as a linear combination of one or more independent variables. Okay, we'll go with the simplistic representation for it. We'll take an example and try to understand what's happening. Okay, so logistic regression is basically trying to predict a categorical variable. And to give a perspective of what linear regression was, linear regression is basically, predict a continuous variable. So what happened was, to give a recap, in linear regression, we discussed about the number of rooms determining the price of the house. So as and when the number of rooms increases, the price of the house increases. We showed a linear trend over there. So it was trying to predict the price, and price is a continuous variable. In this case, we're trying to predict a categorical variable. Assume you have a number of rooms as your factor whether to buy or not buy a house. So before we get into that, let's see what happened in linear regression. We had our x variable as number of rooms and our y variable as the price. The only difference here is going to be if we have x as number of rooms, or you can keep any other factor as well. We'll just go with the rooms. And your y variable will be either not to buy the house or to buy the house. Yeah. So based on the x and y variables that we have here, what essentially it tries to do is, let me just redraw the graph. What essentially it's trying to do is it's trying to divide the outcome into categories. Assume I just draw a graph like this. So there's some kind of threshold that's happening here. Yeah. Here you would say buy the house. I'm just going to draw everything as of now and then explain. For clear understanding, let me just redraw. So this is your x variable and y variable. Remember, x is the number of rooms that you are interested in to buy the house, and your y variable is whether or not to buy the house. So assume I just draw a graph like this. At a glance, you can say this is obviously not a linear graph. So this is not something a linear regression will try to solve. But let's put a pin on that, and let's try to analyze what's happening here. Now, since this is your number of rooms on x-axis, assume this is like around 5 rooms, then 6, 7, 8, so on, and this would be 4, 3, 2, 1. So, and here I'll just put a threshold or a value of 0.5, and here I would put a value of 1, and of course here it's close to 0. So what's happening here is, let's run through a couple of examples. If it's a 3-bedroom house, what is it trying to say? It is pushing the output to 0. If it's a 4-bedroom house, yeah, it's less than 0.5, so it's very close to 0. If you see the distance here, it's close to 0. Then if it is exactly 5, if it's exactly 5, so what's happening? It's at 0.5. We'll see what can be done. If it's 6, then it's closer to 1. Then if it is 8, then it is almost 1. Yeah. So what is happening is, it will try to divide the final outcome. What was our previous outcome? In our previous outcome in linear regression was price. Here, current outcome or new outcome, what is it trying to do? It is trying to give us a probability. So what is it? In other words, it's just saying, if you have a 4-bedroom house, the chances of you buying the house, or the probability that you would buy that house, is like 0.3, 0.35. And if you have an 8-bedroom house, the chances of you buying that house would be 0.9. Of course, this all is under the assumption that you have a data set which would show, or which would be used to train the model, saying if you have a 7-bedroom house, buy it. If you have a 1-bedroom house, don't buy it. Something like that. So after training, we would get a graph which would be curved in such fashion, such that when you pass in your data, or when you're trying to make a prediction, it will give you a prediction probability. Now assume I give a 10-bedroom as my input. It will give me a very close value as 0.98 as my prediction probability. But if I, at the same time, if I give a 3-bedroom as my input, it can give me around 0.28 as my prediction probability. So what can we say based on this? 0.8 is, a 0.8 is very close to 1, and 0.2 is very close to 0. And we can make a mapping wherein mapping is basically a conversion for us to understand what's really happening. We can say mapping when it's 1, or like when it's a high value, you can say you buy the house. When it's 0, you say no buy. So similarly, assume you take another example like 6. If you take 6 as an example, in this case, we get something like 0.6 or 0.7 as a prediction probability. But since this is more than 0.5, or like very close to 1 compared to 0, this will be turned out to be 1, or it will be round up to 1. And then this would indirectly convert to buy when we do the mapping. So you would buy a house with 6 bedrooms in it, or 6 rooms in it, something like that. So to give an idea of how this 0.7 is getting to converted to 1, or what's happening in this here, everything. So let's go through this phase. You have your data, okay? Then you feed it to your linear regression model. Linear regression model. It will do its thing. As we know, it will calculate its MAE, try to find the line of best fit through multiple iterations. Then, uh, then what happens? This is where the linear regression ends, by the way. Linear regression ends here. Like you would pass in your X value and get your new Y value. This is your like prediction. This is where linear regression ends. If you want to do logistic regression, you would do an extra step of post-processing. You would apply a post-processing function. You would just pass your data through another value. We'll keep it as a function for now. So usually people call this post-processing function as activation function. Activation function, because you're trying to activate a certain kind of value. Now assume my activation function is like my activation function a of x is something like x square, and my linear regression model gives me 3 as the x value, and I pass it through the activation function. This gives me 3 square, which is going to be 9. So from 3 I converted it to 9. So similarly, we would have our regression model giving us some kind of value, and it will be passed through the activation function, which will give 0.7 as our value. So this is where 0.7 comes from. So if there was any confusion in terms of how the prediction probability is coming out to be, so that's how it works. There are some common popularly used activation functions like sigmoid, and there's another activation function called as softmax. One more activation function being relu. So these are common activation functions. This is used for binary classification. Binary classification is a situation that we just went through, when you're either buying the house or not buying the house, wherein you have just two categories. Softmax is for multi-class classification, wherein you have you have more than two categories, like 3 or 3 plus. Yeah. And relu is a kind of activation that we'll just discuss later on, but for now it's just you can explore it later on. So this is what it does. It does a post-processing function and gives us a probability. It gives us a probability value. And based on this probability value, we can make inferences. If we get 0.98 as one probability value and 0.28 as another probability value, of course this is 1 and this is very close to 0. We just apply a rounding function on top of it, and we do the mapping as 1 is buy and 0 is no buy. So this is how we try to solve another type of problem, wherein if you want to make a decision is nothing but classifying your opinion, right? So you are just classifying it whether you want to buy it or not buy it. This is another type of problem. So in short, linear regression is used to predict continuous variable. There is no classification being done in it, like continuous value. So if you given the number of rooms, it just gives you the price. So there is no real inference at the end. You say whether you're gonna buy it or not. That's not being done yet. But if you see in logistic regression, you are doing some kind of category over here. So you're basically putting your analysis into either one of the classes. There can be two classes or multiple classes. Based on that, we can use our activation function, which gives a probability. So to avoid any kind of confusion, let me reiterate over that. So here you can see the data which is used for training a linear regression model, and using this model you can do your linear regression, which is fine, but you apply some kind of post-processing function, which people usually call it as activation function, which will give you a probability. Here is one of the examples. Like if I give you x squared as my activation function, and if the linear regression model gives me a value of 3 for some kind of value, I just pass it through my activation function and get another value. Now, if my activation function was something like root of x, and if I pass in a 4 as an example for simplicity, I get 2, right? So this is some other examples. I'm just showing how activation function works. You're just passing in the value to get different kind of value at the end. That usually is probability over there. So in this case, we get the probability, and then we apply a rounding function or some other kind of maxing function or min function, something like that, basically processing it furthermore, such that, and later on we can map it into human readable format. So this is what is being done. So to clarify one more, linear regression is for continuous value, logistic regression is for categorical value. So that's the basic gist of how regression is performed in machine learning. Thank you for listening.